All right, hello everyone. So now I'd like to talk a little bit about a very deep and important theorem called the impulse change in momentum theorem, the I delta P theorem. And this theorem is exactly analogous to the work change in kinetic energy theorem, or the work kinetic energy theorem, in the sense that they both look at conservation, in this case conservation of energy, in this case conservation of momentum, from the point of view of transfer of energy or momentum to a system. So it's conservation laws looked at from the point of view of transfer. So in this case, the work kinetic energy theorem, the idea is we're thinking about a force acting over a displacement, and that is a mechanism by which nature can transfer energy to a system. And conservation law says that the amount of energy you transfer to a system is the amount by which the energy of the system increases. And in the case of the impulse change momentum theorem, we're thinking not of a force acting through a displacement transferring energy, but a force acting over time, which is the one mechanism by which nature can transfer momentum to a system. And then conservation law applies in the sense that, well, obviously the amount of momentum that you transfer to a system is the amount by which the momentum of the system changes. So in this case, we're applying it to a point particle, and the momentum is just, the mass times the velocity. So that will be the quantity that changes. Okay, so let's just think just of our usual general example of an airplane, say flying in three-dimensional space. And so it's on some kind of trajectory like this, and suppose that that object has some mass m, and there's some time t initial. It's at this point on its trajectory, and its momentum, its quantity of motion, mass times velocity, is of course tangential to the trajectory, so it's some vector in this direction of some length. Okay, so we'll say that that's the initial quantity of motion. So that's P initial, the initial linear momentum. And then it flies through space under the action of various forces, and it ends up at some final time, say T final here. It ends up with some momentum, which again is tangential, quantity of motion in a direction tangential to the trajectory at that point, and well, of whatever magnitude, say P final. Maybe it starts with the smaller momentum magnitude-wise, ends up with the bigger momentum magnitude-wise, and so on. And then at any particular time, say right over here, say this is a particular time t, I don't think we need the position of the particle. No, we don't. Okay, so at any time t here, it's got a momentum at that instant of time, which is p at time t. Now you can see that the momentum of the object is changing, and so the velocity of the object is changing, and so that means that there's some acceleration involved, and the cause of acceleration is net force. Okay, when you add up all the forces that are acting, the net force is the mass times the acceleration. So what we're interested in doing is we're saying we've got a bunch of forces acting on this airplane, and each one of those forces acting over time is transferring momentum to the system. And so what you want to do is calculate the amount of momentum transferred by all of the forces over its trajectory and acting over time, and that will give the total change in momentum, P final minus P initial. So that's the basic idea. So we're talking about forces acting over time. So the first thing we need to do is identify, well, what are those forces acting over time? So you need to draw a free body diagram of the airplane. Okay, so this is, say, part of the trajectory here. And at some instant of time, we're sitting there, and we have various forces that are acting. So there's a force of gravity at that instant of time. There's a drag force at that instant of time, and there's a thrust force pushing forward at that instant of time, and there's some lift that's acting, and that lift is maybe not straight up. You can see the airplane is banking like this, and so there'll be a component of the force that's towards the center of the circle. So instead of just drawing it straight up, we'll draw it a little bit back like this. Okay, so there's a component that's towards the center of this circle. So then there's a lift force produced by the wings. Okay, and etc. So we got a bunch of forces that are acting. And then the idea is that the net force is equal to the mass of the airplane times its acceleration. So if m is constant, let's assume that m is constant. If we assume that the mass is constant, then we can do the following. We know that from Newton's second law, if we add up all the forces that are acting at any instant of time, we'll get some kind of net force. And that net force is what's causing the acceleration. So that's mass of the airplane times the acceleration of the airplane at that instant of time. And then we know from basic kinematics of what's acceleration. Well, it's the time rate of change of the velocity. So that's mass times dv of t dt. And then here's where the assumption that mass is constant comes in. Because the mass is constant, the mass times the time derivative of the velocity is the same thing as the time derivative of the mass times the velocity. Okay, and so then you see, but wait a minute, mass times velocity, that's the Newtonian definition of momentum. Okay, and so you can see that you can write Newton's second law as sum of the forces is equal to the time rate of change of the momentum. Okay, you can also write Newton's second law as the sum of the forces is the mass times the acceleration at that instant of time. So that's actually an important sort of result to just pause on for a moment. So we're used to thinking of sum of the forces as mass times acceleration. Net force is equal to ma. But there's an equivalent way to write Newton's second law, at least when the mass is constant, as the sum of the forces is the time rate of change of the momentum. So you can see directly from this form of Newton's second law that the change in the momentum, if you just multiply both sides by dt, the change in momentum is produced by a force acting over time. Net force, sum of the forces, times dt. Okay, and this form, net force is dp dt, is actually in some ways a more fundamental way to write Newton's second law. And certainly when you get to the level of general relativity and so on, then really you're just strictly talking about momenta it's actually a momentum density. And the time rate of change of the momentum density has to do with gradients of pressure and stresses and things like that. Right? So anyways, so be really familiar with, or be aware of the fact that you can write Newton's second law that way as well. Okay, so then what you do is you take this first way of writing Newton's second law, and you just multiply both sides by dt. So then the right-hand side becomes, where do I want to put this? Let's put this over here. Becomes dp at an instant of time t. So that means the change, the infinitesimal change momentum, say when the airplane moves from here to here, from time t to time t plus dt, the momentum will change infinitesimally from the momentum that it had at time t to the momentum that it had at time t plus dt. So there's an infinitesimal change in the momentum. Okay, and that infinitesimal change in the momentum is equal to the net force at that instant of time times the time interval. And then what you do is, so that's the change in the momentum of the airplane from this time to this time. Okay, and then you just add, well, what's the change of momentum from this time to this time, and from this time to this time? And so just starting at the very beginning, t initial to t final, you can add up all those changes in momentum to get the total change momentum. Okay, so you integrate both sides. The left-hand side is integrated from the initial momentum of the airplane to the final momentum of the airplane, which is this guy. Okay, and that's equal to an integral, a sum of the net force times dt. So we're integrating that. The integration variable is time. We're integrating that from t initial to t final. Okay, so we have that. And then the left-hand side here is equal to, we're just adding up the little infinitesimal changes in momentum that occur along the way. And if we add all those up, what we get is just p final minus p initial, which is delta p. So we get delta p on the left-hand side. So that's by definition p final minus p initial. So the finite change in momentum, final vector minus initial vector, as opposed to just infinitesimal changes. And that is equal to this integral on the right-hand side, which we call I total. So that's the total impulse. Okay, that's the total impulse that all of those forces deliver to the airplane as they act over the time interval from t initial to t final. And that total impulse that's like the work done changes the kinetic energy. This is the work done is the amount of energy transferred. Well, that's the change in the energy. I total is the amount of momentum transferred, and that's going to be, of course, the change in the momentum of the airplane. So I'll just write it down here. So what is I total? Okay, so just like work total is, you just take the net force acting over a displacement and you add that up. Here you take the net force acting over time, and that will give the total impulse, the amount of momentum transferred. So that's equal to the integral of the sum of the forces, the net force, over time t, from t initial to t final. Okay? And sometimes, and I'll just sort of give you an example to illustrate this in a second. So sometimes we say, okay, yeah, these forces that are acting over time, the net force, can be a complicated, the net force is just one vector, and it can be a complicated vector that's changing with time. And that complicated vector that's changing with time, acting over this whole finite time interval, will produce a certain change in momentum. It'll change the momentum from p initial to p final. And then you ask the question, well, what if instead of having this complicated net force acting over time, what if we replace it with an equivalent constant force acting over the same time interval from t initial to t final? And we choose that equivalent constant force as the force acting over that same time interval will produce the same change in the momentum, will impart the same impulse. Okay? So we also sometimes think about finding a constant effective average force that, if acting over the same time, would produce exactly the same change in momentum from this p initial quantity of motion to this p final quantity of motion. So that's F average. So if we have that average force acting over the same time interval, where delta t here is t final minus t initial. Okay? So this guy here is called the impulse delta P theorem. And you can see it's exactly analogous to the work kinetic energy theorem. Instead of forces acting over displacement, transferring energy, we have forces acting over time, transferring momentum to the system. Okay? And of course, however much energy you give to a system is the amount by which the energy changes. However much momentum you give to a system, that's the amount by which the momentum changes. So that's the content of conservation of momentum. And also, I really need to point out here, you always need to think, great, we have all these forces, and they are acting on these objects, or on this object, and they are imparting momentum. But momentum is a conserved quantity. So all of the things together that are applying those forces and transferring some momentum, it's a vector like this, to that airplane. Well, it must be the case that the momentum of everything else in the universe, everything else in the universe must be this vector, so that the change in momentum of the whole universe, or an isolated part of that universe that contains the airplane, that change is equal to 0. So we know from here, just sort of a little corollary here, is that, and the change in the momentum of the rest of the universe is, of course, negative delta P. Okay, because, when you apply a force to an object, then sure, you're going to transfer, you apply force to an object acting over time, you're going to transfer momentum to that object. But by Newton's third law, there's a force acting back on the thing that's applying the force. And so the momentum transfer to that object is the negative of the momentum you transfer to that object. And so it's always the case that total momentum is conserved. Okay, so such that the change in the total momentum is equal to 0. Okay, so this is thinking of conservation of momentum from a transfer point of view. This is thinking of conservation momentum from a total momentum in an isolated system can't change. Okay? And so let's think about sort of a somewhat sort of general kind of an example here. So suppose that we were to think about the net force. The net force is a function of time. Okay, and it's actually a vector function of time. There's an x, y, and a z component. So let's plot, say, for example, the x component of this. And it's hard to plot a vector function of time. Let's just plot, say, the x or the y or the z component. Okay, and typically, you deal with situations that might look something like this, where before some time t initial, say the force acting is equal to 0, and then all of a sudden, say the force turns on. So you got a shopping cart, and you start touching the object, you start pushing on it, you push on it for a little while, then you take your hand away, and then the force stops. So at some time t initial, the force starts, and it grows in strength, bigger and bigger, it reaches a peak, say, and then goes down like this. This is very common for, say, collisions, collision-type forces. Okay, so this is what, say, the x or y or z component of the force looks like as a function of time. And so the time interval here, delta t, is t final minus t initial, is this interval. And then the idea is that this force is acting over time. It's going to impart momentum. Okay, and so we just need to integrate the force over time to get the impulse, the momentum transferred. So the area, this integral of the net force over time, is the area under the force versus time curve. And so we're really looking at this area. And this area has three components, the x and the y and the z components. I'll just write area as a vector, meaning the x, the y, or the z components of that. So that area under the curve, well, what is it? Well, what you do is you just take, the x or the y or the z component of the force, and you integrate that over time. And that area is the total impulse, okay? The total amount of momentum transferred to that object by that net force, okay? And then, so what's this idea? So that's this idea. So what's this idea? So that idea is we say, well, rather than having this complicated time-dependent force acting over time t, from time t initial to t final, and imparting that momentum, what we're going to do is we're going to say, well, what is an equivalent constant force that would transfer the same amount of momentum to the object? So we want the force to be constant, so it has to just be a straight line, and we're talking about area. So what we need to do is think about, well, what's the area of this curve? The area under this curve, it's some value. So we want to find an equivalent sum of forces average, so a constant vector, and such that that constant vector acting over the same amount of time from t initial to t final produces the same change in momentum. So in other words, the area under this rectangle needs to be the same as the area under this more complicated curve. Okay, so that's the idea. So we just find that vector, sum of forces average, such that if that equivalent constant force were applied over the same time interval delta t, it would produce the same change in momentum. Okay, so this is the change in momentum, which is p final vector minus p initial vector. Okay, so yeah, so we've got that. And so, so let's just compare, just sort of summarize this. Let's compare this impulse change in momentum theorem with the work kinetic energy theorem. So recall the work kinetic energy theorem. So the change in the kinetic energy of a point particle that has a bunch of forces acting on it is equal to the work done by the net force. So the sum of all the individual works done by those individual forces, force acting through displacement. And so we write that as an integral of the net force at any instant of time, vector dot product with dr. And we integrate that from the initial position to the final position. Okay? So this is a force acting over a displacement, changes the energy. And in fact, we can change this delta k to actually delta E, whereby E here we mean actually like the relativistic energy. So we mean, this E is the rest energy, which is a constant, plus the kinetic energy. Okay, just to make it look more similar or more easier to compare with the other formula. So then the other formula, which is the impulse change in momentum relationship. So the change in momentum, what causes a change in momentum is when you impart impulse. Okay, and that impulse is imparted not by a force acting through displacement, but a force acting over time. So you just take the sum of the forces, the net force at any instant of time, and you integrate, over time from t initial to t final. And I suppose actually to make this integral a little bit more sensible, what you would do is say this is a function of position. So this is the net force at any particular position along the path. Vector dot product with dr, integrate along the whole path. This is the net force at any instant of time along the path, and then integrate over the time. Okay, and so you see there's clearly sort of a space-time duality here. So here we're integrating over time, here we're integrating over space, and as we said in the last lecture, energy and momentum. Energy is essentially the time component of the four-dimensional momentum. It is in a four-dimensional space-time, 3 dimensions of space, 1 dimension of time. Energy is the time component of the momentum. Actually, energy divided by c is the time component of the momentum, and this p are the 3 spatial components of the momentum. And so they are completely dual to each other, and they're both very, very powerful theorems. This is one equation, and this is 3 equations. And so they are equations. If you know, for instance, all of the forces as a function of time, you can integrate to determine the change in momentum. Or if you know the change in momentum and all of the forces except one, maybe one's a really complicated force and it's very hard to do the integral, but if you know the total change in momentum and you can add up the other, the impulse imparted by the other forces, then you can get the impulse imparted by, say, a very complicated function of time. That sort of thing. So it provides an equation to solve a sort of initial condition, final condition kind of problem. All right? Very good. So, so now we'll do an example of this. Okay, so I'd like to do a simple example of how it is you apply this impulse change in momentum theorem. And this will be to the case of, say, tennis. Okay, so you have a ball coming in like this with some quantity of motion in that direction, and then the racket hits the ball, exerts a force in that direction over time, and it will impart momentum to the ball, and the momentum will change from this direction to this direction. The ball will fly off in that direction. Okay, so the picture then looks something like this. So we start off with a ball. We'll call this object number 1, and it has some initial momentum, some quantity of motion that's directed to the left of some magnitude. And then we have a racket. This racket is in motion here. So we've got a racket, tennis racket, and this tennis racket is being swung like this and is in motion. We'll call that object number 2. There's basically going to be a collision between those two objects, a brief but strong as in forces collision between those two objects. Okay, so this ball is zipping to the left. And then when the racket and the ball come into contact, the racket strings are going to exert a strong force on the ball. And so that's going to compress the ball. The ball will compress like this. And that compressed ball is like a spring. It will push back and exert a force back on the racket. So there'll be a force F1, 2, force on 1 due to 2 in that direction. And the effect of that force acting over time is to transfer momentum to the ball in that direction. It used to have momentum that way. Momentum gets transferred to the ball in that direction until so much is transferred that in fact it reverses the direction of the momentum and the ball flies off that way. And of course, at the same time, because momentum is a strictly conserved quantity, if the momentum of this guy changes, well, then the momentum of that guy has to change by an exactly opposite amount so that the total momentum of the isolated system remains the same, remains constant. Okay, so yeah, so in this, when the ball and the racket are in contact, then the racket looks something like this. Okay, and the strings of the racket get stretched like this. They're under tension. Okay, and the ball is compressed like this. Okay, and so there is the racket strings. Just take a racket and push on it. It's like a spring. It pushes back. Okay, and so this stretched racket, these stretched racket strings under tension are exerting a force on the ball. So there's a force on the ball, number 1, due to the rackets, number 2, which is maybe a complicated function of time. It starts out small, then it grows, and then it drops back down again. Okay, but by Newton's third law, of course, this ball is compressed, and so it is exerting a force back on the racket strings, and that force is of exactly equal magnitude and opposite direction. So we'll call this F2, the force onto the racket due to the ball. That's F21. And so I'm going to sort of write this down here. So the force acting on the ball due to the racket, this F12, that force, of course, is a force in that direction, and so there's an acceleration in that direction. So this accelerates the ball to the right, because that force is due to the stretched strings, and the force due to the compressed ball acting back on those strings, well, that force is in that direction on the racket. The racket is swinging this way, but there's a force that way. There's a velocity this way, there's a force that way, and so it decelerates, it slows down the racket. So the racket might have been swinging like really fast just before it hits the ball, and then in its intermediate point, it's swinging a little more slowly, like this. So this F21 decelerates the racket. Okay, very good. And so, or another way to think about this is we have a force acting on the ball over time. It's transferring momentum to the ball in that direction. And then the force that's acting on the racket in turn is transferring, over time, is transferring momentum in that direction to the racket, slowing the racket down. Okay, and then so after the interaction is done, so the racket has now swung over, looks like this, and the strings are now flat again, and the racket is now moving even more slowly than before, but the ball now is, say, whipping really fast to the right, and so it has some large quantity of motion to the right. So this is the final momentum of the ball to the right. Okay, so so that's our picture, and we want to apply this idea of conservation of momentum. And in this case, we're thinking about it as transfer. So we're focusing on the ball and thinking about, well, the amount of momentum transferred to that ball, the impulse imparted, well, that's going to be the change in momentum of the ball, P final minus P initial. That's just conservation of momentum. Momentum is always conserved. Okay, so delta P, what does that mean? Well, it means P final minus P initial. So we're subtracting two vectors. So what are those vectors? So P final is a long vector to the right, and we're subtracting P initial. P initial was a short vector to the left. Okay, and so we're subtracting a vector to the left. That means we add the negative of that vector, which is flipped to the right. And so it's this original vector added to this vector flipped around. And so then this is the change in the momentum. So you had to change the momentum. The final momentum is, big and to the right, but it started off small and to the left. So the change in momentum is, first you have to, reduce this momentum to zero, so add some momentum that way, and then more momentum that way to get a final momentum that's, that long, right? So that's the idea. Okay, and so what is that? So according to the impulse change in momentum theorem, the idea is that the change in momentum of an object, in this case the ball, is equal to the total impulse imparted to that ball. And that total impulse, what does that mean? Well, you impart momentum, a force acting over time imparts momentum. And we're talking about, possibly multiple forces here. It's always, we want to write down the net force. Okay, so we want to write down the sum of all the forces, and we want to integrate that from T initial to T final. So in this case, what are the forces acting? Well, so T initial, T final, what are those forces? Well, clearly, there's the force that the racket exerts on the ball. So that's the force on the ball, number one, due to the racket, number two. But there's also another force. I just want to sort of point this out. While the ball is in contact with the racket, sure, the racket is pushing to the right on the ball, but there's also gravity acting on the ball. Gravity is always acting on things. So there's also a force of gravity. And that force of gravity is, of course, constant. And so you want to integrate that. Okay, but now here's sort of an important point, and this is very common with collisions. Okay, so in the case of a collision like this, the collision forces first of all, are of very short duration, like maybe a few milliseconds, a few thousandths of a second, that the ball is in contact with the racket. So first of all, they're short in duration typically. But more importantly, they are typically huge, very large in magnitude compared to pretty much any other force that's acting. So in this case, and we'll show a particular representative example of a tennis ball hitting a tennis racket, and you'll see that the force that the racket exerts on that ball for that super short time interval is super large, way larger than the gravitational force. So very often, when you're looking at all the forces acting, you can just ignore all of the forces except the collision force. That's the biggest force by far. Okay, so to a very good approximation, in this case we would be able to ignore the gravitational force. It's negligible. It's negligible. It has a negligible effect on the change momentum. I mean, you can think about it as, the collision acts for a very, very short amount of time. During that very, very short amount of time under free fall, how much would the momentum of the ball change in the vertical direction? Well, negligible compared to the huge change in momentum in the horizontal direction. Okay, so this is negligible. So we'll write that sort of formally as the magnitude of the gravitational force is much less than the force of interaction. Okay, and then this force over here, F12, we'll give that sort of a special name. This is the collision force. So we'll call this F collision. And it's in general, a complicated function of time. Okay, so that's great. So this change in momentum of the ball from that small momentum to the left to that large momentum to the right, so this change in momentum is caused by this force of the racket acting on the ball acting over time. Force acting over time, transfer of momentum, and it's basically the collision force, that F12 acting over time. However, it's true that, of course, the ball has changed momentum, but momentum is a strictly conserved quantity. So it must be that the racket has changed in momentum by exactly the opposite amount, so that the total momentum is always the same, never changes. The total momentum in an isolated system never changes. So this is delta P for the ball, okay, but delta P for the racket must exactly equal negative delta P for the ball, such that the change in the total momentum is equal to 0. Okay, so that means that this racket had lots of momentum to the right before it hit the ball, and now it has less momentum to the right. Okay, so there's been a change in momentum of the racket in that direction, okay, which slows down the racket, and the racket's moving more slowly here. And then, of course, when you put the racket down and you're now sitting here at rest, well, the initial situation was a ball coming, you were standing there at rest and a ball was coming at you, and then, later on, you're standing here at rest and there's a ball moving away from you. So there's been a change in momentum of the ball, right? So, but momentum is strictly conserved. And so where'd that momentum go now? Well, it's in the Earth. So now the Earth has absorbed momentum in the opposite direction. So momentum is always strictly conserved. And it's actually a really good exercise in all of these problems to think carefully about, if the momentum of something changed, well, what was the corresponding negative change in momentum so that the total momentum remained the same, so that momentum was conserved. And very often it's the Earth that absorbs momentum, right? If I take a table like this and I've got some object sliding, it's initially got momentum, right, to the left, and then it slides and there's friction and then it comes to rest, and now it's got no more momentum. Has momentum been lost somewhere? No, momentum is strictly conserved, whether there's friction or not. In every possible circumstance you can that exists, momentum is strictly conserved. So the ball used to, or the block used to have momentum to the left, and then it comes to rest. Well, now the Earth has an additional momentum to the left. Okay, so momentum just got transferred from the ball to the Earth. How'd that transfer happen? Well, there was a force acting over time. There was a force of kinetic friction that the block exerted on the table in that direction, acting over the time that it was sliding, which transferred the momentum from the block to the Earth. Okay, momentum is never lost. Okay, let's keep that in mind. All right, so now let's actually sort of think a little bit about, let me just get rid of this, give a little bit of room here. Okay, so we'll sort of draw kind of a typical kind of situation. So this collision force, in general, collision forces are very large in magnitude, as I said. There's just a force in the x direction, so let's not make it a vector. Okay, we're just looking at the x component of the force as a function of time, that collision force. And, what it looks like is, generally like it's 0 until the ball touches it. And then when the ball touches it at some time t initial, then the racket starts exerting a force on the ball. The strings start to stretch and exert a force on the ball. And of course, the ball starts to compress and exert a force back on the racket. But we're interested in the force of the racket on the ball, this collision force. Okay, and so it'll start at 0. And then as the strings stretch more and more and more, it'll exert a stronger and stronger force to the right until it reaches a maximum value, a maximum amount of stretching. And then, of course, it will unstretch, and it will exert less and less force as it unstretches until eventually the racket strings become flat again, and there's no force that the racket exerts on the ball, and then the ball just leaves the surface of the strings. So we have that, and there's a total time delta t over which, an elapsed time delta t over which that collision force is non-zero. Okay, and so this, let's just leave it at that for now. So then the idea is, as we said before, so the change in the momentum of the ball, well, what causes a change in momentum? Well, a force acting over time. So it's equal to, the collision force in this case, as a function of time, acting over time from t initial to t final. And so what that means, it is the area. It's the area under the force versus time curve. Okay, and so we can think of this, again, equivalently as, rather than having this complicated time-dependent force acting over time to transfer a certain amount of momentum to the ball, to change the momentum from this to that, from p initial to p final, what if we said, well, what would be an equivalent constant force that could act over the same time interval from t initial to t final to transfer the same momentum? And the amount of momentum transferred just depends upon the area under the curve. Okay, so we could replace this complicated time-dependent function with a constant function. Okay, and this is F collision average. F collision is small initially, and then large in the middle here, and then small. Well, there's an average. And the average collision force, you choose its value so that the area under that, if that force acted, it was constant for the time interval from t initial to t final, it would impart the same momentum, have the same area under this rectangle as the area under that more complicated function of time. Okay, so this is the same as F collision average, a constant force acting over that same finite time interval. Okay, and that is equal to, the impulse imparted to that ball, transferred to that ball, the momentum transferred to that ball. Okay, very good. So let's throw in some numbers here, because it's kind of cool. These forces are actually huge. So let's call this F collision peak, or maximum. Okay, and so typically these are huge. Okay, so let's just take a simple example from tennis. So we say we start off with, say, a ball, a tennis ball, moving to the left at, say, 20 meters per second. And then when you whack it with the tennis, after you've whacked it with the tennis racket, so let's suppose that it's moving at 50 meters per second to the right. And let's suppose that the mass of the tennis ball, you can look this up, they're about 60 grams. Okay, and let's suppose that the time interval involved in this collision, the time interval, the time during which the ball is in contact with the racket, so the time from here to here, those times are typically extremely small. If you think about collisions between two cars, it's an extremely short amount of time that they are in contact with each other. Okay, so this is, say, delta t is typically, something like 5 millisecond, 5/1000ths of a second. Okay, so then we calculate, well, it used to have some quantity of motion to the left, mass times this velocity. It ended up with some quantity of motion to the right, mass times that velocity. There's been a change in momentum. How much? So the change in the momentum to the right is equal to, well, mv final mv final, that's the final momentum, minus mv initial. So if you put in these numbers, this is 60 grams, is 0.06 kilograms, and convert all to SI units, 0.06 kilograms. And then what you're doing is V final minus V initial. So V final is 50 meters per second to the right. Subtract V initial. V initial is negative 20 meters per second. So it's minus 20, so you get 50 plus 20 is 70. Okay, and so that's why the change in the momentum here is this final one minus this initial one. So let's add the negative of this. And so this is 50 plus 20, so this V, okay, times the mass. Okay, so then you work that out. Make sure, because there's lots of like double negatives here in this kind of momentum stuff. Okay, and so what you get, this number turns out to be, let's put it up here, 4.2. So that's, well, this is 7 times 6 is 42. So 4.2 kilogram meters per second. So that's the change in the momentum, which is a vector directed to the right. And so then we can work out, so the average, what is the average force? So we now have the change in momentum. We were given enough information that we could figure out the change in momentum. So what we might be interested, and we also know the time interval. Okay, so we might be interested in, well, what is the average, the effective average force that that racket exerted on that ball while they were in contact with each other? Well, we can figure that out. So F average, the average collision force is the total change in momentum divided by the total time. Okay, and so what is that? So that's 4.2 kilogram meters per second divided by the time. 5 milliseconds is 0.005 seconds. Okay, and so you crank this out, and what do you get? You get 840. And if you work out the units, of course, you get newtons, because this is a force we're talking about. So 840 newtons. Now, this is an interesting number. 840 newtons is a lot. Is a large force, larger than you might expect. And so to really sort of drive home the point, let's work out. Let me go back over here because we're running out of room a little bit. Okay, so let's imagine that the force versus time curve, which might be complicated like that, let's simplify it, and let's suppose that it looks something like this. It's just a triangle. So the magnitude of the force ramps up linearly with time and then ramps down linearly with time. And yeah, and this is 0.005 seconds. And so what we know is the average force, that's this. That average force is 840 newtons. That's the average. And then we might be interested in, well, what's the peak? So this is F collision peak, or maximum. So what is that? Well, from this picture, it's easy to see that because these are straight lines, it must be that F max, F collision maximum, is just twice 840, which is 1680, or around 1700. So this is 16. This is twice F collision average, which in this case is 1680 newtons, or around 1700 newtons. And you remember that to figure out the weight of somebody, it's just mass times g, and g is around 10. And so this is basically the weight of a 170 kilogram person. Okay, so that's a pretty massive person. And you can imagine that if a person were to apply that kind of force, were to stand on top of a ball, a tennis ball, well, that tennis ball would get squished like this. So in this middle picture, which we erased here, you know, we had the racket like this, the racket strings were bent, and that ball was definitely compressed, because it's compressed by the amount of essentially someone with a mass of 170 kilograms standing on top of it. And so if you look at the high-speed motion photographs of these sorts of collisions, these sorts of interactions, the ball in question deforms like quite a bit, like surprisingly a lot. So that's kind of cool. So key point here is that collisions are are typically very short in duration, and they involve very large forces, larger than pretty much any other force that's present in the situation. And so the impulse imparted, the change in momentum, is really just due to a very good approximation, just to that collision force acting over time. All right? Very good.